Netherlands, so he did his diploma work and his PhD in Groningen, right, with, I guess, a short stay in Berlin along the way, and so working with Savatsky and also Daniel Chomsky, and then after, I guess, a postdoc in Stuttgart, he moved on to faculty positions, and then he had an extended stay in Leiden. That's where I first met Jeroen, and I was very impressed by my interaction with him. And since 3 years, already almost 10 years, 7 years, okay, Jeroen has been director of Solid State Physics Institute in Dresden. And Jeroen has done many important things. I just to mention he works in such fields like graphene or like Dirac materials in general, spin physics, orbital physics, one-dimensional systems, topological excitations. He is very famous for his seminal contribution to the theory of resonant X-ray scattering. That's something that Martin introduced in the 10-minute talk, but I would say at least to me it was very important to see Jeroen's paper, because I remember going to a few of the experimental talks and they would always sort of wave their hands and explain what they see, but I couldn't really understand what was measured, whereas he really started bringing clarity into this field. And that's what his lecture will be about. But before I finish, I want to point out that there are several kind of unusual things about Jeroen. So he is actually extremely good in making physics clear and accessible to sort of people with sort of not as high-level education, not basically the college. So, for example, he has a wonderful article on how to explain spontaneous symmetry breaking to undergraduate students. And it's so good that I often use it, when I have to explain this to the class. And he's also the first physicist that I know who has a Twitter account. And I just asked him, okay, well, so isn't it a lot of pressure? You have to produce something for Twitter. He said, well, okay, you just, every time you publish a Nature paper, you tweet about it. So, I guess it shows, he publishes enough Nature papers, to keep his Twitter readers busy. So, okay, we're pleased that he agreed to tell us and explain, give us an overview of Brink's experiments. So, welcome.
Thank you very much for the very kind introduction. It's a great pleasure to be here. It has been a great pleasure, and I will still be here for a month or so. And I've learned a lot and enjoyed the interactions also quite a bit. So as you understand from Eugene's introduction, is that I don't Twitter that much. Or I can also say the Nature journals have expanded enormously. Okay, today I'll talk about, can you get the light? Oh yeah. I'll talk about resonant inelastic X-ray scattering, focusing on high-density cuprates and magnetic iridates. So it's work done by people at the Leibniz Institute for Solid State and Materials Research in Dresden, and also the Technical University, which are the people here, group members and former group members, and also with colleagues from different institutions all over the world. All over the world. Mainly also experimentalists. And one person that will be here tomorrow is Young Kim, who will give a talk actually on resonant inelastic X-ray scattering on iridates. Okay, so what is resonant inelastic X-ray scattering, or RIX? It's X-ray scattering, obviously, photon on your solid, photon coming out. It's inelastic outgoing frequency or energy lower than the incoming one. And the important thing is resonant, which means that the incoming energy is tuned to an atomic absorption edge. What can you measure? And I'll get a more detail what it is, and also explain it on somewhat more formal level introducing some equations for it. But what can you in principle measure in resonant inelastic X-ray scattering and on a solid? Well, the low energy, let's say at 50 millielectron volt and below or so, in a solid you have the phonons, they can be measured by RIGS. At some higher energies, there are also magnetic excitations, magnons. I'll show you also those can be picked up by RIGS. Then at still higher energies, and you have excitons. For instance, an exciton of an electron that goes from one 3D orbital to another 3D orbital, which is a DD exciton. Also those can be picked up by resonant inelastic X-ray scattering. And then, perhaps even at higher energy, there are charge transfer excitations, where charge is transferred from one atom or one ion to another ion, one atom to another atom in a solid. Of course, these energy scales for different materials can be different, but the point is, all of them, in principle, have a finite RIGS cross-section. And today, I'll concentrate on two types of excitations, magnons and DD excitations. So now in the picture, what happens? For instance, if you do RIGS at a copper KH. What does KH mean? KH implies you start with an electron and deep into the core, so a 1s electron, you add 9 kilo electron volt energy to it with a photon, and you promote it to a 4p excited state, via a dipole interaction. Now, in copper system or cuprates, this 4p state is normally rather high, far above the Fermi level. It's tiny v above the Fermi level. But anyway, the electron sits there, excited electron sits there, the core hole is in the 1s orbital, and after some time, the 4p electron decays, fills the 1s orbital, or you can also say you create an exciton, the exciton decays, and after decay of this 1s 4p exciton, X-ray photon is emitted, and the system is left behind with some finite momentum that the photon has lost to it, and some energy that the X-ray photon has lost to it. Now, this is a KH, and at the copper KH, we talk about indirect RIGS. Why? Because these 4p levels are rather high above the Fermi level, and you do not directly probe the excitations of the electrons around the Fermi level. You can do this, however, when you switch to the copper LH. If you have a copper LH, you will not start from a 1s level, instead you start from a 2p core state. This 2p core state is is of course at less binding energy. In this case, it's around 1 kilo electron volt for a copper LH. And if you start from the 2p, of course, the dipole transition brings you into the 3D states. So by copper LH RIGS, you put the electron out of the 2p core into the 3D state. It sits there for a while, and then a d electron decays, emitting an X-ray photon that then has lost energy, and that energy has been transferred to the 3D electrons of the system. And this is called direct RIGS because you directly probe the valence electrons. And nowadays, Martin said that the resolutions are close to 30 millielectron volt, which is true. I was kind of conservative here. It's better than 100 millielectron volt, which is quite an achievement because the energy loss is 10 to the power 4 smaller than the energy of the incoming photon.
Do you think it will be improving as time goes on? Or is it down?
Yeah, so it will be improving. So the first RIGS experiments I will show you were done by with 100 millielectron volt at Swiss light source. RIGS was a rather obscure technique, it was one beamline. The Swiss were very, I think, had a very good sense of what is, they thought about their science case and they did this, where nobody was really out there doing RIGS. After some of this stuff I'll show you, and especially after we showed theoretically and they found experimentally that you can do spin flip RIGS, there have been, I think now 6 beamlines. So there are 4 still being built to do rigs. The most, ESRF, now I've seen data, but actually has 30 milli-electron volt resolution. So but that's really like a month ago. And the most ambitious one is Brookhaven, that aims at doing rigs at the copper LH, at 10 milli-electron volts. So the European colleagues say that's over-ambitious. The American says it.
So that's going to determine the size of the detector because it gives you some time of flight.
Well, there's no time of flight because photons fly. But the yeah. So they tell me, and yet, so now the arm of the detector is about 10 meters. So you're 10 meters away from where the photons have hit the sun. And what becomes now important, for instance, is purely mechanical stability issues. That the concrete floor is not thick enough, stuff like that. So it's really becoming. So I would say this 10 milli-electron volt with the technique that they tell me, with the present state, also on the analyzers. The CCD analyzers are very important. So if the sensitivity of this, with the sensitivity of the CCD analyzers cameras that they have now, 10 milli-electron volt is the limit. But, you know, okay. Direct and indirect rigs, now in a different picture, referring a bit more to bands. So direct rigs, photon goes in, it's excited into the valence band, an electron out of the conductor band fills the hole, photon is emitted. The scattering, in this case, I would say, occurs via absorption and emission matrix elements, basically. At least in leading order, that's what happens. If I have indirect rigs, it's a bit different because now the photon comes in, excites the 1s electron into the 4p state high above the Fermi level. And while this core hole is present, the core hole here scatters electrons at the Fermi level, makes electron hole excitations there. So it's the potential of the core hole that gives rise to low energy excitations. And after this core hole interaction, this electron that was just a spectator decays again, and the photon is emitted, leaving behind this electron hole excitation. So in this case, the scattering occurs, so the inelastic scattering occurs via the intermediate state core hole shakeup. That's one way of calling it. Okay. So now you would say, well, you know, that sounds a bit complicated. And actually, that's what kept many people off from theoretically considering rigs, and also the experimentalists, except the Swiss ones, from starting to do these experiments. Because it's, well, I have ground state, I do X-ray absorption. In X-ray absorption, I have a core hole, I shake up all my electrons, I come into an intermediate state that's complicated, then I do, in this intermediate complicated intermediate state, I do X-ray emission, and I end up in the final state. I have a local atomic transition, X-ray absorption, and a complicated state with a strong core hole potential in the middle, and then again I do a local atomic transition. So, the local atomic transitions, of course, contain all chemical detail and are completely atomic specific. So now you have a problem that's very specific and complicated. So there's not a problem you want to have, right? However, there's the following argument, which now in hindsight it's easy to make, but you know, 10 years ago, people did not consider it at all. In the end, RIGS brings you from a ground state to a final state. This final state is only slightly perturbed. It carries the low energy, long wavelength, elementary excitations of the solid. Wild things can happen in between. I don't care really about it. I can learn about the low energy, long wavelength excitations, which means that RIGS can probe universal effective low energy behavior, at least in principle. X-ray absorption cannot, because in X-ray absorption you have a final state with a strong core hole potential which has perturbed your system way beyond a small perturbation of the ground state. So this is now, in principle, a good thing. So how does it now work in terms of some scattering formulas? It's a second order scattering process. So the red amplitude is given here, depends on the outgoing photon is given by prime, and this is the momentum of the outgoing, momentum of the incoming photon, the polarizations of incoming and outgoing photon, and the energies of incoming and outgoing photon. The following way, you start with the ground state, you act with the absorption operator, you get into an intermediate state. From this intermediate state, you act again with the absorption operator, or its conjugate, you emit a photon, you can end up in the final state, and in because it's a resonant process, you divide by the denominator, which contains the intermediate state energy. And this Rix operator, in principle, is the well-known operator. In leading order, you can get rid of this exponent here, and it's just a dipole operator. So polarization cross P, dot P. So let's think about this. There are also quadrupolar positions, but let's forget about it. Okay, so the Rix intensity is just this amplitude squared and a delta function conserving energy of the system. That's okay. I can even rewrite this a little bit more and introduce a Green's function. So this intermediate state already looks like a kind of Green's function. It's 1 over zk minus h, which is the sum over this intermediate states and this denominator. And this Green's function is just the intermediate state propagator with this z defined in the following way, and this is the core hole lifetime here. Okay, with that my equation even simplifies more. So my Rix amplitude is a dipole operator, an intermediate state propagator, another dipole operator, and then acting on your final state. Yeah.
Can I just ask, so you just taught us this formula, it goes back to 25, Chalmers and Heisenberg. Obviously, they didn't have Rix experiments going on. Do you know in which context, or?
It's just the second order, so it's scattering. So it's you know, it's
really wrong scattering.
Yeah.
So that intermediate state, it seems that you excite the system, the momentum rearrange, the energy levels rearrange, so you drop the electron back down. You think the amount of energy it loses or the amount of momentum it loses has to be significantly different. So when it shoots off the X-ray, you're not really getting the ground state information.
Okay, that's right. You don't get ground state information. You get information of the ground state, to which you have added a little bit of energy and maybe quite a bit of momentum. So you get information about the ground state, the excitations, low energy excitations above the ground state. Actually, when I talk about it now, it's amazing, because 10 years ago, people would ask, how can you have momentum conservation? You make this intermediate state. It's completely perturbed. Photons will come in to screen the core hole. They will carry momentum. How can you be sure there's anything like momentum conservation going on? It's an impurity, strong impurity that you make there. And again, I mean, that's an argument to put the whole problem aside of thinking, okay, the first time that momentum conservation was showed, where one could show that there is a dispersion of the magnons, which we know from neutron scattering, and was also measured by Rix, people were actually surprised by it, or many people in the community had not appreciated at all that that would be possible. And why is momentum? Okay, good. Let's just, any more questions? Okay, so having now a little bit of theory in our hands, we can ask how does it work actually experimentally and theoretically for different systems. And today I want to talk about basically 3 different materials: quasi-2-dimensional cuprates, quasi-1-dimensional cuprates, where you can do orbital and magnetic excitations, observe orbital and magnetic excitations in Brink, say a little bit about quasi-two-dimensional iridates, where you can do the same thing, and then end with a problem which I think has not been solved yet. Well, the paramagnons in doped cuprates have been observed. I don't think there is consensus yet in the community what these excitations really are. They have not been observed so far with inelastic neutron scattering. They might be related to magnetic, they might be related to charge. And what their relation to superconductivity is also not clear. Okay, so now let's just, for very simple-minded, look at a cuprate, and I'll took lanthanum 2 copper 04 for you, which is basically the fruit fly of the ITC materials. It's a not superconducting material, but it's a parent compound of a high TC, the high TC cuprate superconductors. It has this copper oxide layers, copper O2 layers, separated, in this case, by lanthanum oxide layers that are kind of insulating and where nothing's going on, and then another copper oxide layer where, when doped, the superconductivity emerges. So let's look at the magnetic structure of lanthanum 2 copper 04. There are spin 1/2s sitting in the plane. Here are the spins. Between the coppers there are oxygens connecting the two copper spins. It actually is an insulator, in spite of the fact that I have one electron per site, or an odd number of electrons in the unit cell, where band theory tells you that if you have an odd number of electrons in the unit cell, you should have a metal. But it's an insulator, and we know quite well why. Because if an electron, or in this case a hole moves from one copper site to another copper site, this becomes occupied by two holes, and they repel each other severely by a Hubbard U, which is in the order of 60 electron volts or so. Okay, so the electrons are not able to move due to this large energy penalty. The system becomes insulating, therefore, and a gap opens up of about 2 electron volts. Okay, it's a strongly correlated antiferromagnet. How does the local copper 2+ environment look like? So the most simple-minded picture to understand that you can get from chemistry, where you look at the cubic crystal field splitting of a copper 2+ ion, which has 9 d electrons, so one hole, as I mentioned before, sitting in a cubic surrounding of negatively charged oxygens. These negatively charged oxygens split up the local states for the local 3D states. So in principle, kind of 10 electrons, I have 5 times 2 states for the d electrons, and this 5-fold degeneracy for the ion is split into a set called T2G orbitals, and the other ones are called EG orbitals. I'm sorry for this names, that's historically what they are called. So these are the T2G orbitals. They are all filled, these planar orbitals. The EG had 3 electrons or one hole. This elongated one, the cigar-shaped one, is filled, and the hole is in the x² minus y² orbital, which I've indicated here, the hole with now a spin. So that's where the hole is sitting. Actually, if you distort this octahedron, or as an experiment, it is distorted in lanthanum 2 copper 04. These apical oxygens are moved away from the copper. This will result in a splitting, actually. The splitting of these T2G levels. These two guys will split into a orbital doublet and orbital singlet, and these EGs will also split, and that causes the 3z² minus r² to be filled here, and the hole to be in the x² minus y². So that's all, say, local, well-known local chemistry for copper 2+, for lanthanum 2 copper 04. What do you learn? Well, the hole in the ground state sits in this x² minus y² orbital, and in an excited state it can be in any one of those orbitals. So let's now calculate, for this simple case, the amplitude, the Rix amplitude, which is this thing with the intermediate state propagator in there. Now you say, well, these transition matrix elements are dipole elements. I understand them well. This intermediate state is a complicated thing. Can I get rid of that some way, or in an effective way? So that's what I'll do now, and discuss the ultra-short core hole lifetime expansion. It deals with this Brink's function in the middle in a very naive way, but at least it's the first thing to do, the first thing to look at. So we have to think, we have to remember that there is a short lifetime tau of this high energy core hole in the intermediate state. I make this core hole, and actually it will tend to decay by lots of different processes. It can Auger decay, another inner shell electron can fall in, kicking out another electron, and actually it can fluoresce in many different channels. So it's very unlikely it does this Rix process. It's much more likely the core hole has disappeared by another scattering channel before the electron that was up there can fill it again. So that makes the core hole very unstable. It lives for a very short time, which means that in the denominator I have a large core hole broadening, this gamma, which is basically 1 over the core hole lifetime. So that maybe I can use. If I look at the Rix amplitude, there was this Z in the middle there, and there's my core hole lifetime from this I gamma into the amplitude. And if I'm naive, I could say, well, actually, let's make gamma the largest energy scale in the problem. So then Z becomes large. If Z becomes large, I can neglect this En. And if I do so, now I have a summation that's just closure, and my GZ will be constant. It is naive, but let's try, see, and use it and see what happens. And actually, much of the theory of Rix is based on going systematically beyond this naive approximation. So in this case, my Rix response is governed by dipole transition operators. I just can look what this does for me. And here, you can write down the formula, but also you can actually write it down in a figure. And that's what the PhD students and postdoc did in 2012. They said, okay, I can understand it in the following way. These are my D states, down there are my P states. I have this Q graph, and I have to make 3 moves on this Q graph to understand the Rix process. For instance, I start with a hole in the x squared minus y squared hole. Now the first move is absorbing a photon. For instance, with polarization EY. So start with polarization Y. I end up in a P shell, in a P core hole with PY character. Or you can say, I have a hole in x squared minus y squared, the hole is demoted into the core by the absorption. Now I make a second move. For instance, the second move can be to do the circle, which means picking up a constant, C1. Okay? And now the third move is emission, and if I emit a photon with polarization Y, I pick up another constant, and I end up in a 3z squared minus r squared orbit. So you see, I can get from x squared minus y squared to 3z squared minus r squared if I know the polarizations and I know these numbers that I pick up there. And this is true for any DD excitation in my system. Does this work? Well, here are the D.
So this way you're going from far away from a single band model, from the covered model, because you're saying that you really make an excitation when the hole left behind is in some very low-lying orbitals. And this EG orbitals below T to G, and now you're saying that the hole left behind after you refill the core state is in one of the EG orbitals, and is it still?
No, okay. So I'm saying I didn't draw the core. Now if here is my core, I have 2p. I come in with an electron. It has to go here in x squared minus y squared. Right? And I'm saying I just showed there's the amplitude for getting now this electron here, or this up electron filling the core.
So, okay, so it's still EG, but it's a lower line EG. Right?
Yes.
So at least single band covered model.
What's the energy difference between the xy minus y x squared minus y squared and 3z squared minus 3? R squared.
Yeah, so that depends on the local chemistry. It's not the same for all cuprates. And one-dimensional systems can be different from two-dimensional systems. It's on the scale of 1 eV, 1.5 eV. Actually, I gave this talk where Daniel Chomsky was present, the PhD supervisor, and I told him actually, you'll see it in the data, that sometimes the T2Gs can be, this EG can be below the T2Gs. So actually the lowest possible orbital excitation are T2Gs. And so this is completely impossible. This violates all kinds of intuition and ideas. But Brink has proven it to be true, actually. So this local, say, quantum chemistry of these orbitals is really intricate. And
But splitting of EG, that's just because from Q to Q it's like elongated.
so why is it much more complicated? Why is it complicated? So you say, right? I mean, if I have a cubic system, now I do this, it becomes tetragonal, and I know that this is splitting between that I've shown. But well, we are in a cuprate, and it's not a cubic system to start with. I have my lanthanum oxide layers here, above and below, and these cause long-range modulum-like potentials on the local copper side. So even if I have a perfectly cubic octahedron locally, the longer range interactions, the longer range potentials split up already the EGs, and also will split up the T2Gs. And also the covalent character of the bond in plane and out plane is different. And also this will make the in plane and out of plane orbitals already inequivalent, independent of this oxygen cage surrounding. So to your question, how large is that energy? Let's look at the data. So here you see the excitations. Actually, yeah, this is the EG. This is 3 Z squared minus R squared, which is highest in energy. These are T2Gs. And it's about 1.7 eV to 2 eV, around 2 eV. And these data, these are represented as a function of angle of the incoming and outgoing photon, which translates into the polarization or the dot product of the polarization of incoming and outgoing photon. And you see that the theory that I've represented in this rather naive triangle diagram works really very well. And the reason for that is actually it's all geometry. If I know my matrix elements, the rest is geometry, and that's the geometry of these orbitals, and that's what you pick up in the experiment. Okay. So the comment would be interesting. There are these EV excitations. They are 1 or 2 eV above the thermal level. Who cares about them? Because they're high energy with respect to any temperature that you're interested in for superconductivity. Maybe they do something effective to the low energy degrees of freedom, but it can never be much because they're so far away in energy. And that's basically right. That's a correct argument. Now, let's look at the low energy features of this antiferromagnet. The low energy excitations of this antiferromagnet are, of course, magnetic, and they have the spin waves. Canarics pick up the spin waves. And naively we say, well, I wouldn't know how to do that. I wouldn't know how an X-ray photon can just flip its spin. Well, maybe by its magnetic field, but this magnetic field is so small, I can forget about that with respect to any other process. And why should it be enhanced as resonance? There's no reason for that. Well, there is. So now let's look at the same picture as I did before, but now introducing the spins. So now here's the hole in the x squared minus y squared orbital. This is now a filled other T2G orbital or EG orbital. And here's the core. I come in with a photon, promote a down electron out of the 2p core into the 3 shell. Okay. Now what can happen is that, as I've shown before, that the down electron out of another orbital can fill this core hole, emit a photon, and by DD excitation. That's okay. And now let's look at this intermediate state now for a bit. Actually, I have a spin 1/2 into a 2p state, which is an angular momentum L equal 1. So I have a spin and I have an orbital momentum. And I have spin orbital coupling in the core. Actually, spin orbital coupling in the core of, in this case, a copper ion is huge. It's about 20 electron volt. It's not a small perturbation. It's order 1. It's leading order. Meaning that spin is not a good quantum number, L is not a good quantum number, because L dot S is so large, J is a good quantum number, or loosely speaking, if I spin half, it continuously exchanges its spin angular momentum for its orbital angular momentum. So the spin half is as much up as it is down, roughly. So well, actually, if this spin that's sitting here is as much up as it is down, when it is down, then a up electron can decay out of this D shell. And what I've done is a spin flip. I've effectively flipped the spin of this 3D electron sitting there at the valence band. So now the point is, again, I did rigs. I had some complicated intermediate state with the core hole. This core hole has spin orbit coupling. All fine, but the end result is very simple. I started with a spin up, and I end up with a spin down. It's just like neutron scattering, effectively. Yeah? And you can do this in iridates as well, but then you will be in the hard X-ray regime. It will be 11 kilo electron volt or so, and the energy of the photons will be. Anyway, so that's also in this diagram. In this diagram, I start now with an x squared minus y squared orbital, where the hole sits, do an absorption into the py. But now, instead of making a small circle here, I go along this line, and I pick up an operator. This operator is SZ. It's a spin operator. It's a spin operator acting on the electron in the x squared minus y squared orbital. So the z-axis is a real axis in my system. It's the axis perpendicular to the xy plane. This z operator acts on my spin. I end up in this x orbital, and now in the decay, again, I go to x squared minus y squared. So I go from x squared minus y squared to x squared minus y squared, but pick up the spin operator, and if the spin in this orbital is not parallel to z, I can make a spin flip. If the spin is parallel to z, then of course I do nothing to the spin. So this was, we pointed out that this is possible. In 2009 we pointed out that this is in principle possible, and also that this process is absolutely leading order. It's just, the intensity of that should be just as large or comparable to the DD excitation energies. It's leading order because the spin-orbit coupling is huge in the core. Okay. So, in special cases, direct spin-flip scattering is allowed at the copper edge. And now it turns out, we are very lucky, all cuprates are special cases. Special cases, I mean, spin in the XY plane. Now, this is the first experiment of lantern to copper 4 by Brink and Jeroen, the Italian team that really was leading, and still is leading in this team. So here, at 0, I get photons that have lost 0 energy. That's my 0 loss. I'm not interested in that. These are elastically scattered photons. At about 100 millielectron volt, I have a phonon line. That's also fine. But now look at 300 millielectron volt, I have a huge peak, which is the magnon actually. It's the magnon of lambda 2 copper 4. And then at some higher energy, I have multi-magnon excitations as well. This is the magnon dispersion as measured by Riggs. So this is momentum, this is energy. The dots are the Riggs data that I've shown you before. And the blue lines, actually are not fits to the data, but the blue lines are the results of neutron scattering. And you see they're perfectly nicely on top of each other. And we understand not only the energies, this is here, this is the intensity. We have also calculated the theory for the intensity, the Riggs intensity of the micron excitations also confirms or compares well to the experiments, where intensities are much more difficult to calculate than energies. So this is really nice. It shows that with X-ray photons, you can measure the spinels. And then you say, well, that's good for you, but neutron scattering has done that for ages. So you learned something about your technique. You didn't learn anything about lambda-2 copper 04, which is true.
One question. Do you have a sum rule for it?
Good question. I don't know of one. Making it more complicated, because in inelastic neutron scattering is very nice. It has some rules on S of Q and omega. So here we measure S of Q and omega times some prefactors. And these prefactors are the problem preventing you to write down a strict sum rule, or actually any sum rule.
And how would you know? How can you compare peaks then?
How?
I mean the intensity. If there's no sum rule, you could in the experiment just get the height wrong.
Well, the experiment is always right.
Right. In theory.
Yeah, yes. So, okay. The one, so you I think also with or without the sum rule that problem remains. But not having a sum rule makes it more complicated. And what you can do, actually, I didn't point it out, but looking at polarization dependence. So if the polarization in and polarization out is the same, it means that the photon has not lost any angular momentum to the system, which means it cannot have made a spin flip. If you are in cross polarization, you know any excitation that the photons have picked up have to involve some transfer of orbital angular momentum, or angular momentum, to the system. So if you would, in an ideal world, would be able to flip the polarization of or measure the outgoing polarization, you would see the speed disappearing if you have parallel polarization and popping up if you have. But
this doesn't give you the intensity, which is it's checking consistency because it is for magnetic or non-magnetic.
yeah. So yes. So but of course you do have form factors. Right? So
yes, neutron scattering, they typically calibrate on phonons.
Yeah.
They're saying they know cross-section on phonon very well. That gives them the intensity for this spin flip.
right.
Can you say they'll calibrate on something else?
No. So if we, of course, if we would have complete control, we would easily calibrate on the DD excitations, which intensity we would know, and then also we could figure out what the intensity of the macrons is without relying on this kind of simplistic approximation to the intermediate state propagator, etc. But at the moment, I think that's, we will say, nobody really tried. Nobody really tried. It's harder than neutrons for sure. Yeah.
So the prefactors are momentum dependent?
Sorry, the what?
The prefactor to SQ omega are momentum dependent?
Yes, in the following sense. Or then, so what happens actually? Their momentum in this case is the momentum transfer to the solid. Now, if you want to transfer different momentum to the solid, normally what you will do, you will change your incoming and outgoing like this. But if you change your incoming and outgoing photon like this, then your matrix element to make a transition from the 2p state to the 3d state also changes. Because your polarization with respect to this, say, p orbital changes. So that's actually the geometric factor that I've shown you before. So it is angular dependent, and that
In your own way.
in its own way. Yeah. And it's definitely also energy dependent, which is really a nightmare if you would like to calculate that. It depends on the incoming energy. Okay. How much time do you want? Okay. So I do the 1D cuprate, skip the iridate, and do the dopant cuprate. So the 1D cuprate actually is, that we looked at is this system that has chains pointing towards you. And in these chains, they consist of copper of 4 plaquettes connected to each other at the corners where there's an oxygen sitting. So it's a one-dimensional chain, which is nice, of copper 2+. Because we know that in the one-dimensional chain, my excitations are not magnons, they are spin-ons. They are fractional ones. So this is the Rig spectrum of this chain system. So here's momentum transfer, this is energy transfer. So you see at high energy transfer, there are the orbital excitations. These are my T2G orbitals, and again here, my EG, so the 3Z squared minus R squared is. So this we have seen before, the orbital excitations. Down here, you see that our spin excitations, they go up to half an EV or so. They are relatively high energy. So these are the spin excitations of the spin chain system. So now we know very well what those excitations are. They are spin-ons, and you can calculate them in principle from a beta ansatz, from the beta ansatz solution of the 1D Heisenberg model. And this actually is what Jean-Sébastien Coe did. So this is the data. This is energy transfer, so lost energy for different momenta. And you see there is a nice set of dispersing excitations, but they are always broad. There are tails here. And those tails actually are the textbook signature of spin-ons, of continuum excitations. And here, for 3 momenta, I've shown the data, the calculations, which says model, which is the beta ansatz solution of the Heisenberg model, which gives you the green line. And then if you take the beta ansatz solution, put it and add the resolution to it, convolute it with the resolution, you get this red line, which basically is on top of the data. So here, I think this is a textbook example of spin-ons, which again is nice, but is not something physically new. Neutron scattering has measured those spin-ons, not in this material because they are at higher energy, too high energy for neutron scattering, but it has measured them. Okay.
So you're saying that this material cannot be measured by neutrons in principle, or they just or what?
So neutron scattering is best when it works, when you have the highest fluxes if you had thermal neutrons that have an energy of 300 K, 25 millielectron volt, that's it. Here you see that the spectrum is significantly, goes up to 500 millielectron volt. So with the thermal neutron doesn't have just enough energy to scatter, to produce that kind of energy. So you would have to go to neutrons with higher energy, which they tell me is possible, but that's experimentally much more difficult. Fluxes go down, essentially. But the simple solution for them is to go to like a potassium copper fluoride, which has then an energy scale for the spin-ons of like 20 millielectron volt or even below. And there, if you just cool it down, you'll also see the, of course, the spin-ons. So talking about neutron scattering and rigs, let's compare. So I have 3 sets of issues that I want to compare. First of all, is the material needed. So for neutrons, I've written down large. For inelastic neutron scattering, you need probes, you need samples in the order of grams. Rigs, actually, some of the data I've shown you was done on thin films, cuprates. My experimentalist friend tell me they can do rigs on a single copper oxide layer if they want to. That's something that neutron scattering will never be able to do. So rigs is very good. it's very good at, say, probing magnetic excitations, spin excitations of objects that are of the nanoscale.
How much insight will they need for single layer?
Not so much. Actually, as a single layer is quite okay. It's quite okay. Yeah. So there's Mark Dean wrote a paper on that, and it was done within the normal beamline.
1 to 2 days.
Yeah. Yeah. So, and it will be better. That was at Swiss Light Source. At the ESRF, it will be better. At Brookhaven. So it's so for people interested in oxide heterostructures, for instance, RIX is a perfect tool. Neutron scattering is a very inelastic neutron scattering is a tool that does make quite sense for that. So that's a good thing for RIX. The bad thing is magnon energy is accessible. Well, high energy is not a problem. Low energy magnons, well, you have to take care of your resolution, which is hopefully 10 million electron volts in a year or so. If Brookhaven holds its promise, but still very low magnon energies will never be accessible by RIX. Neutrons can measure parts of electron volts, billion electron volts. This will never be accessible by RIX. Neutrons are best, as I said, at low energy. Now let's look at materials. Good thing for neutron scattering is that you can do it on any system. You don't have to think about it. As long as your system does not absorb the neutrons and sets off a nuclear reaction, you're fine. RIX, as I said before, it depends on all chemical, on each chemical element. It's a different edge. There can be different physics going on there. And I'll skip now the iridates. But one reason to look at iridates with RIX is exactly this problem. So iridium is a very strong neutron absorber, and therefore very bad for inelastic neutron scattering. While for RIX, actually, it's perfect. Okay, let's not go through that now, and just finish with the open problem, which is the doped cuprates. I'll just show you the data, and then leave it at that. So, magnetic rigs at paramagnets, which is relevant for doped quasi-two-dimensional copper oxides. So this is one of the first spectra taken again by the Milano group. It's on 80% doped lanthanum strontium copper 04. 8% LSCO has a TC of 21 Kelvin. These measurements were done just below TC. TC is an energy scale that's not relevant for the Drake spectrum, because here you see energy losses in the order of EVs, and here's the momentum transfer. So what you see at 2 EV, again, is this DD excitation that we have seen already a couple of times. And it's not momentum dependent, and it's sitting there in the doped system just as it was sitting there for the undoped system. Okay, but now let's look at the low energy scale. This looks like a magnon that is dispersing. It's just like in the undoped system, a nicely dispersing magnetic, well, you don't know if it's magnetic. It doesn't come with the label magnetic, but it's a excitation that's dispersing just as the magnons were in the undoped system, but now in a non-magnetic system, in a paramagnetic system, actually in a superconductor. So is this now some strange effect in LSCO? Might be, can be different for other systems. Well, it's not. This is the paper of Keimer's group, Le Tacon, in Stuttgart. So intense paramagnon excitations in a large family of high temperature superconductors. So here is their data. On the left, this is the undoped system for them, this NVCO. The different spectra offer different momenta. So zero loss peak that stays there. But you see at the finite energy there is the magnon that's nicely dispersing out, just as it was as in undoped lanthanum 2 copper 4. Okay, that's good. Now, these are doped systems. This is weakly doped and more doped. This is, I think, even on the overdose side. And you see for all these systems, at any doping, the maximum peak remains. It sits there, it becomes broader, but it does not go away. Now,
What were the different curves?
sorry.
Delta,
So delta, for them is an angle, but is the momentum transfer to the solid. It's just K.
okay.
Yeah. So if for some angle would be K equals 0, the magnon would coincide with the zero, would go to 0. So the conclusion is that if you look at the magnon dispersion for the undoped system, and now you go to a doped system, you actually find back excitations that have a dispersion that look exactly like those magnon excitations, but they're broadened somewhat. And we also know now for some systems, for the electron-doped systems, actually they are hardened, so the energy of those excitations is a bit higher than for the undoped system. For other systems, it's a bit lower, but they remain. Okay, so then you can say, well, let's do what was the first theory done for it to explain this. At least numerics was done that found a similar effect by the Stanford group. So what they did is calculated the dynamical structure factor for the Hubbard model, just S of Q and omega for the Hubbard model, with quantum Monte Carlo at high temperatures. So the idea is, this is a disordered spin liquid system. If you go to high temperatures, the peaks are broad anyway. Maybe that's not that important that we do a simulation at high temperature. Let's just go with that for the moment. Then for the undoped system here, n equal 1, you see that again there are 9 momentum. So this is momentum now is on the vertical axis, on the horizontal axis energy. So you see nicely dispersing branch out here if you go to pi 0, and also when you go to pi half, another part of the Brink zone, you see well-defined magnon until you go to pi, where you, of course, you pick up the antiferromagnetic break, which is not there, but there is a lot of spectral weight there that is anticipating the antiferromagnetisms that will set in at lower temperatures.
So this calculation done on a finite cluster.
Yes,
How big was this?
I don't remember.
12 size.
I can look it up.
Judging by the number of points, you might guess that the 8 layers or something.
You would say between 0 and pi, there are 1, 2, 3, 4, which are 8. Yeah.
Well, but not yet.
Okay, I'm not trying to say that their calculation is correct or not correct, but at least it gives us something to compare to. Well, the data is correct, but the approximations are so severe that they I can't say anything about it. So now let's look at the doped system. And at least what they see for the smaller cluster, the high temperature, is indeed there is something like a paramagnet. This is 15% whole doping, and the magnetic excitation when you go to pi 0 remains. When you go to pi half, also the magnetic excitation actually becomes more pronounced. Yeah? And even if you go to 40% doping, which is quite a lot, there in S of Q and omega, there is spectral weight there.
It's kind of very bizarre. So paramagnet is pi 0 direction. Pi is easy to understand. Pi 0 is not so easy.
Okay, you know it. Yeah, it's true. It's my next slide. But you can go to another system. And now this is VSCO. This is the data Marco Brioni, actually. Here he is. And PFL. And Lausanne. Now, this is not doped, undoped system. This is an under-doped system. This is optimally doped VSCO. superconductor. So these are now two directions. This is again a momentum going to pi 0. So from momentum to pi 0, sorry, from 0 to pi 0, and here momentum going from 0 to pi pi. For the undoped system, I have my nicely dispersing magnon sitting here in both cases, as it should be. That's all right. Now let's go at the underdoped system and look at the dispersion in the pi 0 direction. In the pi 0 direction, yes, there's a paramagnon. Even if we go to the overdoped system, again, in the pi 0 direction, there's a paramagnon. If I go to the pi pi direction, however, I see that, well, I would not see much evidence. There is some spectral weight here, but it's really not the paramagnon that you see in the pi 0 direction. This can be related to the presence of an electron hole continuum, which is a very good argument to make, because if you have an undoped system, you say, what are my low energy excitations? Well, I have just spins, they can make magnetic excitations, that's all there is. Now, if I dope electrons to it, well, also I have a low energy electron hole continuum out there. This electron hole continuum, also there, as I told you in the beginning, Ritz will make excitations, electron hole excitations in this continuum. So these electron hole excitations that you can make will come in a doped system. They have to, right? But now so they are important. But now the kind of devilish thing is that we see something. But for the undoped system, we see clearly magnons. And now they gradually change, they become wider, they change somewhat in energy, but nothing radical happens upon doping. While you would argue, if it's purely electron hole excitations that kick in if you dope the system, why should this electron hole excitation continua look like a magnon for the undoped system? Why should that be the same? Of course, there are calculations, but there's no a priori argument. So that's what I would say. That's a kind of very unfortunate coincidence or complicating factor if it is that way. Conclusion is that Ritz is sensitive to elementary charged orbital and magnetic excitations of, for instance, cuprates and also of iridates. They can directly probe the dispersion of these orbital and magnetic excitations and also charged excitations, although I didn't show that today. There is evidence, experimental evidence, of a robust paramagnon in the doped cuprates or low energy excitation on the magnon scale in the doped cuprates. Its relation to superconductivity remains to be explained. Its origin, in my opinion, remains to be fully explained. And the next energy scale that, of course, Ritz wants to look at is the energy scale of the superconducting gap, but we are not quite there yet. I hope this promising new technique will give rise to new experiments and hopefully also some new theory along the way. Thank you for your attention.
So maybe just if someone asks about the assumption of the rates, could it be that there is some that the fact that you have this weight shifting from something that is from the paramagnon to maybe electron hole, there is some kind of assumption that makes it shift in such a way that you essentially don't see the fix in around. The sum somehow is fixed.
I would love it. I mean, if anybody can get a handle on that, prove that, that'd be fantastic.
So do you have some explanation for why things look so different in the 0 pi direction and in the pi pi direction in the Fermi surface behavior or something? If it's being damped by electron excitations, can you explain that? Or?
So the obvious way to go is to argue in terms of the Fermi surface, which also I think is actually what has been done. But that relies on the interpretation of these excitations as purely charged.
And that works, you say? Or?
In overdose, yes.
And overdose this works. But then the question would be, okay, I have the uncorrelated quasi-particle, and under the overdope system, I'm very happy with just bands. How do I connect to the antiferromagnet at zero doping?
I have the same question.
In those power magnons, two questions. Number one, I would expect if you do just an absorption spectrum, XAS, you should also see particle-hole continuum. So, and you should not see a magnon there.
Correct.
So can you use that to check the amount of particle-hole fluctuation if it's increasing tremendously? I mean, you should kind of see a difference from that.
That's a good question. So I think it's a good idea to do that. We're working on that. So the complication is that in X-ray absorption, again, you have to score whole lifetime. And the score whole lifetime just broadens all your absorption features because the final state has a very small lifetime. Okay, so if you look experimentally, what the X-ray absorption looks like as a function of doping, it's one peak. If the system is undoped, it's a somewhat broadened peak and a somewhat broadened peak, but still, it's just one peak. Because you have this huge core hole final state potential that sucks in all spectral wave. So but the thing to do would be to look at how the intensity develops. So this intensity can depend, I think, on the coupling to the X-ray to the electron hole continuum. Yeah. So one would have to do an absolute measurement of the X-ray absorption intensity as a function of doping, which nobody has done, and compare that to some theory, your theory, to how a coupling to the electron hole excitations renormalizes that intensity and redistributes it a little bit, but that's not a big effect.
Another question which you sort of referred to at the very beginning of why momentum conservation works. So as I understood the argument, the people who didn't believe it would happen is that the core hole is such a strong perturbation that you would wind up with a final state which emitted tens of phonons and stuff like that. And you're saying, well, no, that doesn't happen. Is it related to the fact that the core hole doesn't last very long?
Exactly.
Therefore, doesn't have a chance to excite multiple excitations?
Correct. So if you would calculate what the sort of phonons so if you would calculate what the intensity is for a phonon loss, yeah, it's omega over gamma to some power squared. I think it's omega gamma squared times the intensity of what you find for magnetic excitations or for DD excitations.
So gamma is big, you say?
Yeah, gamma is in the order of what is half an eV, 250, I think. Now phonons are smaller. So that's the same. That's correct.
Two questions. One, so can they at least compare, like, so you said, oh, let's compare samples at different doping levels. Do we at least have one way of measuring intensity at different doping levels? Or, I don't know, maybe like the whole calibration goes completely different. Can we maybe compare, let's say, D to D transition? Is it the same regardless of the doping level? Can you always reference to that?
So absorption actually is good because you just you measure it. It's an absolute probe, right? You measure how much has been absorbed. So that's great. So there you can measure absolute intensities quite well.
Like, then I want to compare, let's say, I don't know, doping 0.1 and 0.15, right? I get the curve, but let's say how do I, let's say whether I can argue that my Riggs cross-section is going by a factor of 2 or not, I have to have an absolute reference point.
Yeah.
So is there any cross-section that doesn't change as I change doping that I can confidently?
So for Riggs now, for Riggs, you know, people would argue that it's a good idea to normalize on some DD excitation.
So there is a good argument that it does not depend on doping.
It's the zeroth order thing you want to do, because these excitations are because of their energetic separation from the conduction band, they will have little coupling to the conduction band, and therefore their intensity should not much depend on it. But you run into trouble again, because if you have the excitation in the final state, so you have making an exciton in the final state, this exciton, of course, will also be screened by the electron hole excitations in the doped system. But again, you run, but hopefully that screening is of less importance or weaker than the screening of the
So
excitation.
you're saying that maybe what's happening is that as we do more, we also get more screening of this intermediate state that we generate.
Correct.
And the fact that everything has more or less the same intensity is a conspiracy that you get more screening, so you get less of an effect, even though naively you will generate more particle ultimately.
Right. So I think one of the suggestions, or one of the things that at least I suggested to this, like ESRF people, is it was good trying to normalize things on spectral features. But now let's really go towards absolute, them measuring absolute intensities, and us actually calculating absolute intensities. So we do this in quantum chemistry, or at least for the undoped system, you can just get a number out for the Riggs intensity, and try to compare that number to something they measured. So that will be the way to go, because otherwise we always will be making circles, I mean big circles or small circles. But I think for the technique it's important to start measuring, at least calibrating for some materials, absolute intensities. And for us, calculate them.
Question later. So let's thank Jeroen again.